Morning, good morning. All right. So, precious 41 minutes. This is what the plan is for today. So I'm going to call this first part of our lesson Speed and Explain. And that will involve little containers. And I made a set for every kind of grouping of seats. So we're going to take maybe 4 or 5 minutes, take a look at this, and that will help to touch on some things we looked at yesterday, but also some other concepts with solutions. Then I am so sorry that I felt it's no excuse. Shame on me as your teacher that I felt the pressure of the clock. And when I get nervous that I need to explain something and address questions and clear up things, and there's 30 seconds, I flub up. So I want to make sure that we're clear on that very last concentration expression problem. Then I want to look at pages 4 and 5 in your packet, and that finishes the theoretical stuff. Then we'll probably have half of our time, and I want to have us, you can work individually with a team, look at some sample multiple choice. So we'll see at the end of our period, but then you have your packet, and we're going to do these sample problems. If we feel like, okay, we need a day to digest things, because what I'd like us to do just for this is to answer, I think I've assembled 8 multiple choice that are incredibly like what we're going to practice, and you can use those as resources. And one concentration conversion like we did yesterday, and we'll look at, and you have your samples that you can use to support you. And then one, how do you make the solution? Remember, we practiced that. We made them, and then we practiced answering, something like that. Okay, so we'll decide at the end, does it make sense to go ahead and do that tomorrow? And I hope that doesn't distress us. It's not meant to. It is just, okay, can we demonstrate that we paid attention the last couple of days? And then the spec lab due tomorrow. Any concerns, questions about the agenda, any of these items? Okie dokie. So if someone wouldn't mind just going ahead and kind of being the in charge person or the leader with the container of things that I had for you. And so there's a beaker that contains 2 test tubes, and they have different solids. I have them labeled for you. One is sodium hydroxide, one is sodium thiosulfate. Doesn't matter, they're just different. That's all. We don't have to know what they are. And a beaker of just some water. So all I'd like us to do first is go ahead and take and fill up one of the test tubes about halfway, and then the other one, a third halfway. Okay. So my first question. These are both soluble. They're sodium salt. All sodium compounds we know are soluble. How can we speed up the solution process? How can we get the solution created faster? Jacob, give me one idea. Why? So I can't help but always encourage us to think on the particle level. And we take for granted that things have to come into contact to attract. And so we know that in the case of an ionic compound, we are overcoming the electrostatic attraction of the ions. We're overcoming the hydrogen bonding of the water, but that final step isn't going to happen unless solvent comes in contact with the solute. So if we increase temperature directly related to kinetic energy, they're going to come into contact more. Not only more, but what? If we would heat this, what else would temperature help us with? They'll collide more often, but also Okay. I want to talk about touching, if you don't mind. Yeah, that could actually aid to give some of the energy that's needed to overcome the attraction. You're absolutely correct. So if they have a greater speed, that'll help them collide more often. But what else about them touching? So they'll collide more often, but is there another aspect of solute and solvent touching? I think when we get it, it'll become clear. I don't think I'm using a good term to get it. Aaron? Yeah. There's a difference, right? If you kind of like joke around and just give a like playful punch to someone, and then you like give a for real knock them out punch. So they'll collide more often and more forcefully. So increased temperature. What else can we do? I did it. You're doing it. Agitate, right? So if we just flick up the wrist, if we stir, if we shake up and down, what is that doing? How does that speed up solution formation? More touching. Yeah, you're helping solvent that isn't into contact with the solute come into contact. All right. So now that they've had a couple moments, touch the bottom of one, touch the bottom of the other. You can go ahead and pass it to your neighbor. Okay, can I remind us? Physical change. Physical change. I think that this is just awe-inspiring. Just making a solution? Ooh, that's kind of low in temperature and refreshing. That's so warm and soothing. So this is increasing in temperature. This is decreasing in temperature. We know this is endothermic and exothermic. Why? We're making a solution. So why do we even get a change of temperature? And then how can we get one that's endo and one that's exo? Isn't it the same stuff? Well, doesn't this confirm what we looked at yesterday? Yeah. So we know in our humanness, we say 3 steps lead to a solution. Solute attraction broken, solvent attraction broken, solvent attraction formed. In the endothermic, the cost is greater than the payout. Yeah. And in the exo, the payout is greater than the investment. In chemistry, this is what we'd like. We'd like for the process to release more energy than the energy we have to input. Yeah, kind of like the stock market. You hope, okay, if I put in, $100, well, I hope I get out more. It's kind of stinky when you get out less. Often, when it's endothermic, when we're not ending up with lower energetic, if you will, or anthropic substances, then overall in the process, then this might not occur, but it does in this circumstance. Okay, so that talked about as far as how do we impact the rate of solution formation, but also endothermic, exothermic. I have a paper towel in there in case. Hello, sir. Very nice to see you. If you need to wipe your hands or anything. So if you could just put them, I know the beakers are probably still there. If you can just put it to the side. So if there's an empty desk by you, or if you want to put it on a lab bench that's near you, just so it's not in the way. Okay, my next question. So see and explain. So my next question. Okay, here is just a beaker that is holding a solution. How do we know if it is saturated, unsaturated, or supersaturated? Go, Jacob.
You can add more solvent. Or solute.
That would probably be the better way. As it is appearing, I'd add solute. Okay, how does that answer?
So if it's If it's super saturated, adding a little bit more will take all of it as expected.
Super saturated, you are, I know the word manipulation just isn't, a very nice term. So we're fooling, tricking nature. So we talked about that if we would create, so this in your packet is looking at solubility versus temperature of solid solutes, yeah? That if we increase temperature and we make either an unsaturated or a saturated and then decrease the temperature. Not all combinations, but a lot. For example, copper 2 sulfate at room temperature, copper 2 sulfate only to make it saturated will be about 24 grams of copper 2 sulfate per 100 mils of water. But if we increase the temperature, we can get more to dissolve. And then if we cool it down. Now, some combinations, as soon as you start to decrease the temperature, the excess solute will fall out. The solvent and the attraction just won't cooperate. Also, some supersaturated solutions are incredibly stable and do not drop their excess solute. So those of you that really enjoy sweet tea, that's amazing. I think we were meant to drink sweet tea, I guess. You know that sweet tea, oh my gosh. In fact, I think sometimes I see, not that I've heard it, super sweet iced tea in the grocery store and that kind of thing. Man, you throw ice in there and everything else, you're really disturbing that, and the sugar never falls out, does it? So that is an incredibly stable situation. Where some supersaturated solutions, you just maybe walk across the lab, and that's enough stress. We, of course, had the hand warmers that whenever you sent the shock wave through, that caused the excess to fall out. So if you added and a bunch of solute came out, and if we could add one seed crystal, so a big enough piece of, let's say this is copper 2, well, no, it wouldn't be because it would be blue, potassium bromide. And you could see the crystal and then more came out, then we know, oh, it was super saturated. How would it respond, Jacob, if it were saturated and you added more solute?
You would just see just the crystal.
Yeah. So it's holding its max. So no more can dissolve. So that single crystal would fall to the bottom. Well, what if it were unsaturated? Yeah. Taking a look at just, it could be pure solvent, it could be a solution. We have no idea if it's pure solvent, saturated, unsaturated, supersaturated. The only change that would confirm one of those is if we saw undissolved solute. If we saw undissolved solute. So again, if we remember back to the yellow and blue and added the salt, and you shook, and there was a whole bunch of salt still undissolved on the bottom, we needed to add as much salt as we could to make it saturated so we see the separation. That is confirming that at that temperature, with that amount of solvent, it's holding as much as it can. If we would add more solvent, it could, if it were super saturated, be a stress. But that would be the only thing. So I think you meant solute. Yeah. Okay. Questions? Those were the, oh no, there's more. I forgot. All right. So we know with my compliments, ready to have my, low temperature soda and I'm so we open it now. Maybe else for me. So, or the should be this one. That and I have another bottle, so this doesn't cooperate. Okay. We know soda is carbonated. We add carbon dioxide. And as we said, gases, thinking of their behavior, not a lot will remain in solution. So to encourage carbon dioxide to stay dissolved, plus the carbon dioxide, that's non-polar. So we're trying to induce it to form particle attraction. If we lower the temperature, that helps. But there's something else. Whenever you open a bottle of soda, a can of soda, you hear that. And then you see bubbles up. Why?
There's more pressure inside the bottle now, wherever you open it.
Pressure of what? You're absolutely correct. Pressure of what?
Gas.
What gas?
CO2.
Oh. So we can get, so can you see that whenever I let some of the gas out, well, first, this is proof that the gas wants to leave. But when you shake or your bottle drops, you just have to wait a little while before you can open it, right? Why is that? So above soda, to help keep the carbon dioxide dissolved, if possible, on average, usually there's 2.5 atmospheres. We feel 1 atmosphere of air, but there's 2.5 atmospheres of carbon dioxide. So you guys know that this will settle right back in. All right. So the Mentos, we know. Yeah. You can send this yourself, the Mentos and Diet Coke. Oh, Joey, really? All right, we gotta change that. You mind? Okay, can you get a maybe a hand width piece of Scotch tape? That's great. Okay. All right. We're gonna stick the
It's like expletives or whatever, so it's like instead of yes.
Okay, so there it is. I'm gonna open this. This has not been the one that I shook. Okay. Can you just lower the Mentos on the tape enough so the Mentos does not come into contact with the liquid? So that's what the tape will do. So just lower it and then kind of fold it over, and then I'll put the cap back. Okay. So either you've done this yourself or you've seen videos of it. All right. The understanding is that when the Mentos with their peppermint irregular coating come into contact with the artificial sweetener in diet soda and caffeine. And we're not sure if there's other ingredients in Diet Coke. It seems to cooperate with that. So I played around with this with my kiddos, and we tried different flavors of Mentos. The fruit Mentos are and different sodas. You get like this little overflow. But these, yeah, you get a fountain. So you will not get wet unless you want to. Okay, so just let me give you directions. All right, I'm pulling it for everyone to see. All right. Now, what happens is not a chemical reaction. The bottle is not going to blow up. We are not making carbon dioxide. Okay, the same amount of carbon dioxide. Well, we live a little escape. But in essence, when I bought it, it's still in there. Okay. So if you just open it, oh wait, we have to first get them in chosen contact with the system. Oh yeah, go. Oh yeah. So you feel a little pressure on the bottom. Okay, so the carbon dioxide. The understanding is that the regular surface is just a place where the carbon dioxide can collect. So carbon dioxide is like, let me out, let me out. So, you see any bubbles? You open it just so slightly, but then that the what? Carbon dioxide. We're fooling you. You thought you were going to be let out. Look. What the carbon dioxide is doing when it reaches the 2.5 atmospheres again, it pushes that right back in. Okay, you want to see? Tease it again. Yeah, I'll let you out. We just get one out of it. You can do however you want for this next one. Okay. When this was first discovered, this relationship, there were chemists that just did a lot of different creative things. So if you ever go on YouTube, you can look at like people purchase like hundreds of 2 liters of Diet Coke. And they put them on strings and they have music playing and they go and they like, it's just and fun. Okay, what do you want to do? You're in control of the release of the carbon dioxide. I'm totally fine if you do. You don't want to get beat hurt. So here, you want to do over here? Totally fine, as long as you're okay. Now that's only, I mean, what is that, 8 ounces, 6 ounces? I have no idea. So it may just a little bit. Okay.
Shake it.
All right. Now see, we're like, but you're showing. Okay, whatever you. Okay, so better not play around with this. Kids. And the only thing is, usually have to eat make them soft. Oh. We'll try it. I know, but I want to control when it comes into contact and then just have it leave at this small pinhole. Then we should so good. So are you okay to oh
It's about drawing this. So it's.
I'm sorry. Is it okay if we go a minute into homeroom? I'm just going to.
So it's one where you have. You're right. So like it's rectangle. He's drawing it as a piece of color, which isn't. That's yeah. I did more than I did.
I just need to soften it a bit more. And again, like a couple of seconds in the microwave. But I think that's good. Okay, so replace this with this. We'll go to the floor, and then you're super strong, but I'll do the 8 of them. I'll hold it to place, and then if you nope, it'll drop. Oh. Better than just the trickling out. Okay, we'll have to get it better. Friday. So Friday, I say 2 liter. And the landing of the stairs, and let's hit those. Yeah. Well, you know, I'll definitely get them already. Yeah. Good. Unless someone has a different idea for us to do, I'll totally put it up with me. Thank you. All right. So if we will tidy up what I had planned. So I asked you this question about goo gone. Now, goo gone, if you've ever heard of this, yeah. Oh, this is like miraculous. Exactly. So when you say like, what have you?
Pine tar off like that.
Oh my gosh. A bumper sticker off a car. Wonders. It's so annoying. I don't know if you feel when you're removing a label and the sticky, remains behind. Goo gone. Anybody else use? And for what? To accomplish what? Just yeah. So just whenever it's like you need to unstick something. Yeah. And it just all those others just don't seem to work. But if you take a look, the ingredients are not shared with you. So how understanding what's going on? We're not performing a chemical reaction. What do we know about goo gone and its ability to interact with the pine tar or interact with the adhesive? What must be true? That's what this question was asking of us. So as far as polarity and intermolecular forces, adhesives, pine tar, ionic? Do we have an understanding of like what would it be? Ionic? Would it be covalent? Usually most natural sap, I say we could say carbon-based compounds, they're probably going to be covalent. The majority of covalent substances, polar, but there's a whole lot that aren't. So the success of goo gone is the molecules have a polar and a non-polar end, just like soap. And so any of the non-polar stuff, it will attract. Any of the polar stuff, it will attract. So it's just been maximized, if you will, to be able to do the job that we need. All right, this is conveying what Joey demonstrated for us. So How do we get more carbon dioxide to remain in the soda? We increase, the pressure above it. We could decrease temperature, but also pressure, but it's of that gas. So, if, I don't know, you have an oxygen tank on ya, you think, oh, I need to like recarbonate if I get some oxygen in there. No. So it has to be that gas that's over it. All right. Okay. Could you answer this, please? Sorry, I didn't number these pages. It's the page before all of the concentration expressions. Okay, easy peasy. Solubility per temperature. For KNO3, first off, this is a double whammy with being soluble. All potassium compounds, all nitrate compounds soluble. Ionic, so we know what it'll dissociate. What's the shape of the graph? You want to show me? Yep. As we increase temperature, solubility of solid solutes. Ionic compounds we know are all solid at room temperature pressure. But O2, and I would automatically, now we don't know what these temperatures are, but in comparison, the solubility of gases is much less than ionic compounds. So if these are similar scales, I would definitely, I mean, the most important thing is that we're trending downward and we're trending up, but I definitely say we can, dissolve more. Okay, vapor pressure, the pressure a vapor exerts on the liquid it vaporized from. So if the blue ovals are representing water molecules, we know they should be really Mickey Mouse, but we'll go with it. The presence of the solute lowers the vapor pressure. Why? And I've chosen the visuals that I've chosen for a reason. When I got my chem degree, we had a different theory, a different proposal. We know when we measure the vapor pressure of water when it's a sugar solution, that the vapor pressure is less than pure water. So we know that happens. That's not in question. But the question is, why? So the thought was, well, we know a bunch of these waters, if it's a solution, are attracting sugar and the sugar is attracting them. And so because of that particle attraction, the water's held back from leaving solution, but not so much anymore. We look at the solute. If it is homogeneous, if a solution is truly homogeneous, then we know not only is the solute equally distributed through the solvent to make the solution, but it's also present at the surface. And it's like a roadblock. So if a water molecule gets enough energy to overcome hydrogen bonding, and it's gonna free itself, it might knock into that sucrose and then lose its energy. Now, if it knocks into this one, it probably is gonna give that one the energy and then it leaves. So there's less surface available. So the vapor pressure of the solvent with the solute present is lower, or the vapor pressure of a solvent with a solute present, because of the presence of the solute at the surface. Now, we learned in honors chemistry consequences of that. So because we've lowered vapor pressure, that impacts the freezing and the boiling point of solvent. The boiling point of a sodium chloride solution is greater than pure solvent, and the freezing point is lower than pure solvent. We don't have to know that. We got that in honors chem. We're not asked to prioritize that. But this has consequences in our real world. But this could be asked of us. What is the impact of the solute on vapor pressure? It's lowered of the solvent. Okay, my total bad. I apologize again. I was silly to feel the pressure, to let the time pressure me. Silly, silly, silly. So can I just bring us back? I had shared with us the answers to number 2, and I believe that some of our molarities were not matched. Okay. You are given the molality. We don't have to memorize these equations. I will give them. No worries, no worries. Okay. Molality is mole of solute per kilogram of water. So we're told this is the concentration in molality, but we're asked for molarity and then mole fraction of the solute and the solvent. All right. Well, how do I get this to this? And we are given the density of the solution in gram per liter. Okay. Well, why don't I assume I have a kilogram of water, so that will then be 0.273 moles of KCl. So if I'm trying to get capital M, I'm going to run with that. Okay, however, 1 kilogram of water is not 1 liter of solution. All right, so if I have a kilogram of water, well, that's going to be 1,000 grams. And respecting the 3 sig figs, I wrote in scientific notation. Okay, I need not just the water, but the solvent and the solute. We are given the density of the solution. So there are 1,011 grams of solution in every 1 liter of solution. Yeah. So I know my grams of water. Can I get how many grams of solute are there? I sure can. So I found the grams of solute, added that to the grams of water. That's my mass of solution for that amount of solute. So then using the density, that will be my volume. And respecting 3 sig figs, 1.01. I wouldn't be terribly hard on the sig figs. And then that's how we get the 0.271. I think, didn't you guys get 0.276? Yeah. Okay. So that molality and the molarity, they get you in that denominator. You can trust that you will be given everything you need, just in what perspective are you in? Questions on that? I will take room time, but I will take 2 more minutes. Take one, pass it on, please. Take one, pass it on. You're welcome. Yes, sir. Oh, did I give you? Oh my gosh. Okay, everyone have. Okay, so could I ask us? Now, we may look like, oh my gosh, I'm scared. This is going to take 5 years. No, 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 no. could I ask that we turn to page 2 and look at what is number 47? These are all out of order. Don't worry about that with the numbering. All right, 47. If you remember the classic safety video in Honors Chem, you're told then when you're making a solution of an acid, you always add acid. Always add acid. But why? Why? So we're just kind of told we do that. If any of you created a sulfuric acid solution, we went over this the other day, it got warm. To create a sulfuric acid solution, the enthalpy of the solution is quite exothermic. Quite exothermic. Okay, so if we have a liter of water and we are adding concentrated acid, let's say it changes temperature 20 degrees Celsius. It's probably going to be more than that. Let's say 50 degrees Celsius. Water, having the specific heat that it does, you have to input a lot of energy to change its temperature. So the potential is there, but water is a great heat absorber. So if we add acid to water, there's a lot of water there that is going to remain and be in excess to what interacts with the acid. If we do the opposite, if we have acid and we add the water that can have a great change in temperature, we'll get that change in temperature, which could boil this, and you have vapor, which could splash on you. That's why we don't do that. Okay? It's all because of this. So the answer is B for 47. Okay? I'm thinking Friday, tomorrow we double period. So I'm thinking going into tomorrow that we address some of these. I'll prioritize the most important ones. We'll be given 20 minutes. You can work in your teams or individual, and then we'll chat about them. Address any concerns or questions, and then start our next journey, which is just wonderful. Okay? And then on Friday, we'll get a 2-liter of Diet Coke and then answer a handful of these. Okay? Good? Wonderful.